It's one star among 300 billion in our galaxy. It's not close to the center of the Milky Way. It's not the biggest star, not the smallest, the brightest, the hottest, or the coolest. It's not even the only star with planets. Class G yellow stars like the Sun make up 1 out of 13 stars in our stellar neighborhood. It's not special in any way, except one. It's the only star we know of that supports life. The Sun is our star. Without it, Earth would be cold and dark. There would be no weather, no life. In fact, there would be no Earth. From the dawn of life and through most of human history, the Sun was a benevolent giver of light, heat, and energy. But now, as we rely more and more on technology, we're learning that our star is more dangerous than our ancestors ever knew. Like most stars, the Sun produces a lot of energy. It produces enough energy in 1 second to power human civilization for 500,000 years. Energy from sunlight enables life to thrive and multiply on the Earth. Nearly all life on Earth is supported by photosynthesis, the process plants use to convert sunlight to chemical energy. Animals eat plants and use that energy too. Those animals are eaten by other animals, and the energy moves up the food chain. The energy in the food you eat originally came from the sun. Most of that energy is light. From low-frequency radio waves to high-energy gamma rays, light is much more than what we see. Visible light is one small part of the electromagnetic spectrum. Photons, which are the particles that make up light, travel in waves. High-energy photons make high-frequency light, like X-rays or gamma rays. Low-energy photons make low-frequency light, like radio waves or infrared. But how does the Sun produce so much energy? To find out, we must look deep inside our star. The Sun has 6 main layers. The outermost layer is the corona. This is the atmosphere of the Sun. It's much hotter than the surface and can be 1,000,000 degrees Celsius. That's about 1.8 million degrees Fahrenheit. Scientists aren't sure yet why it's so much hotter than the surface. It may be due to magnetic activity, but this is one of the big mysteries of the Sun. The next layer is the chromosphere. This thin layer goes from corona temperature to surface temperature very quickly. The visible surface of the Sun is called the photosphere. This is where all of the visible light that reaches Earth is emitted. It's also the coolest part of the Sun, at 5,500 degrees Celsius, or 10,000 degrees Fahrenheit. Just below the photosphere is the convection zone. Here, hot material boils up toward the surface. The plasma at the bottom of the convection zone is around 2 million degrees Celsius, or 3.6 million degrees Fahrenheit. Below the convection zone is the radiative zone. Energy bounces around so much in this layer that it takes 170,000 years for a single photon to escape, even though it's moving at the speed of light. Finally, the core. The heat and pressure in the sun's core are so great that atoms of hydrogen are smashed together to form helium. This process is called nuclear fusion, and it produces the immense amount of energy that will fuel our star over the course of its 10 billion year lifespan. Energy leaves the core as photons. They bounce around the radiative zone for 170,000 years, boil upward through the convection zone, and are finally emitted from the photosphere. From there, the photons travel nearly 150 million kilometers, or 93 million miles, to the Earth in only 8 minutes. The sun emits light across the entire electromagnetic spectrum. But high-energy wavelengths like ultraviolet, X-rays, and gamma rays are incredibly dangerous to life on Earth. How can life survive all of that dangerous electromagnetic radiation? The answer is Earth's atmosphere. The envelope of gas that surrounds our planet blocks nearly all of the dangerous wavelengths of light. The visible portion of the electromagnetic spectrum, the light we can see, passes right through. So do some radio waves, microwaves, and infrared. They help keep us warm. In addition to heat, light, and energy, the sun also bombards the Earth with high-energy particles. These particles come from the corona. This is the solar wind, and it streams from the sun constantly in all directions at speeds of 400 kilometers per second. That's about 1 million miles per hour. If the particles that make up the solar wind reached Earth's atmosphere, they would gradually strip it away, leaving Earth airless and unable to support life. Luckily, the Earth has a strong magnetic field that acts like a shield. It deflects most of the particles from the solar wind. As long as we stay on the ground, humans are fairly safe from the dangerous effects of our star. But with humans and technology in space, things are a bit more complicated. Scientists call conditions in space that affect humans and our technology space weather. It's driven mostly by the sun. Space weather includes the solar wind, as well as solar flares, coronal mass ejections, and geomagnetic storms. We're learning how to forecast space weather. To help, we have more than 20 satellites dedicated to studying the sun. But the most useful tool so far is on the sun itself. That tool is sunspots. Solar storms often start near sunspots, and solar storms affect space weather. Sunspots go through a cycle every 11 years where their number rises and falls. During solar minimum, there aren't many sunspots. Those that appear don't last very long, and solar storms are pretty rare. Solar maximum is a very different story. There can be as many as 100 sunspots on the sun at any given time, and they last for several weeks. Sometimes there are several solar storms per day. So why do sunspots appear? The sun has a large, powerful magnetic field. It extends throughout the entire solar system. This huge magnetic field is generated deep inside the sun, bursting through the surface in long lines and loops. The sun isn't solid, so areas rotate at different speeds, which twists and tangles the magnetic field lines. Sunspots form where the twisted lines emerge from the photosphere. Exceptionally strong magnetic activity keeps the plasma in these areas cooler, which is why sunspots appear dark. Strong magnetic energy around sunspots can drive solar storms. A solar flare like this one is a perfect example. A flare occurs when tangled magnetic field lines suddenly snap and reconnect. This releases a burst of electromagnetic radiation and energized particles, or plasma. Only the largest flares have any impact on the Earth. We're much too far away for the intense heat of a flare to ever reach us. Most of the problems that flares cause are related to technology. The particles and electromagnetic radiation from large flares can cause radiation storms in Earth's outer atmosphere. This might disrupt communication signals on Earth, anywhere from a few minutes to a few hours. Everything from TV signals to GPS, and even cell phones can be affected. Another type of solar storm is a coronal mass ejection, or CME. CMEs are more dangerous. Unlike flares, CMEs can affect technology on the ground. A CME is a bubble of plasma and magnetic field lines launched from the sun's atmosphere. They often start over clusters of sunspots. A single CME can contain billions of tons of material that smashes into anything in its path. The plasma in a coronal mass ejection is especially dangerous for spacecraft outside of Earth's protective magnetic field. Plasma is a super-hot, electrically charged gas. It can damage a satellite's onboard electronics, causing it to fail. Many times, the magnetic field in a CME will be repelled by Earth's magnetic field, similar to putting the north poles of two magnets together. But sometimes the two magnetic fields are attracted to each other. The result is a geomagnetic storm. Earth's magnetic field gets peeled back like an onion, and particles from the sun can reach lower into our atmosphere. This is what causes the aurorae, the northern or southern lights. A geomagnetic storm can also create ground-induced current. This is an electrical charge that travels through large conductors. Things like cars, airplanes, and even trains are safe, but power lines and water pipes aren't. Current traveling along pipes can weaken or even break them. Broken pipes might mean people have to go without water. And even though power lines are made to carry electricity, adding extra current is dangerous. Things like electrical transformers can break down. If that happens, it can take months to replace a single transformer. Parts of the power grid could be shut down. That means no refrigeration for food and medicine, no gas pumps or hospitals. Even running water relies on electricity. A CME might not physically harm you, but think about all the things you use every day that need electricity. CMEs aren't rare, especially during solar maximum, but they're only dangerous if they're aimed at Earth, which is rare. The last time a supersized CME hit Earth, the northern lights reached farther south than Florida. the telegraph system, which was the highest technology of the day, was disabled worldwide. Back in 1859, the effects were minor, but something that size hitting us today would be catastrophic. For most of human history, space weather simply wasn't a problem. It's ironic that the technology that allows us to study space weather makes us more vulnerable to it. But space weather isn't the only threat from our star. As the sun ages, it gets hotter. Anywhere from 1 to 2 billion years from now, the brighter sun will render the planet too hot for most life on Earth today. Eventually, it will be so hot, the oceans will evaporate. Water and air will boil off into space, and Earth will be too hot and too dry for life. Then, in about 5 billion years, the sun will run out of hydrogen in its core. It will expand into a red giant and get so big that it will engulf the orbits of Mercury and Venus, and possibly even Earth and Mars. As the sun works to consume as much fuel as it can, it will collapse and fuse helium into carbon for about 100 million years, until it too is exhausted. At the end, there won't be an explosion. No spectacular supernova. The outer layers of the sun will just drift away, forming a nebula that will disperse in about 10,000 years. That's the blink of an eye in cosmological terms. The core will remain as a white dwarf, spinning and dissipating heat until it eventually falls dark, billions of years later. It seems like such an uneventful end for the star that gave us life. But by the time the sun dies, humans might have moved on to other worlds in other parts of the galaxy. In its time, the sun will fuse elements like carbon, nitrogen, and oxygen, which are the elements of life. The sun will seed the universe with the potential for new life, just like older generations of stars did for our sun. It's a cosmic cycle. Maybe one day, humanity will witness new life on a new planet, orbiting a new sun. If that life is anything like us, they will look up to their